Hey everybody, welcome to our first lesson on stoichiometry. If you haven't read chapter 7.1 in our textbook, you can find it at the top of the web page. I highly suggest you do that. It'll give you a little bit of background in what stoichiometry is. But stoichiometry basically is a way for us to count and keep track of how much reactant and product we should be getting or using in chemical reactions. So that being said, I have three problems here that will help us figure out how to calculate certain things with this powerful tool that we call stoichiometry. So I'll read the first question, and then I'll go through how I solve them. I will show you how to do the full version with ratios, and then I will show you my version of these types of calculations here. So without any further ado, here's our first question. So the first question reads, how many grams of ammonia can be made from 25 grams of nitrogen and excess hydrogen? So the first thing that you'll notice is there's quite a bit of language in these questions. So the first thing you want to do is figure out what the chemical reaction is that's going on here. So in this case, it's basically saying how much ammonia, so we're making ammonia, can be made from nitrogen and hydrogen. So I'm going to go ahead and write out the equation for that. So it's nitrogen gas plus hydrogen gas, and that will produce ammonia as a gas. Now, this reaction, if you look at it right now, it is complete in terms of the chemicals that are involved, but what is missing is the fact that it's not balanced. So we need to make sure that our chemical reactions are balanced. So I'm going to go and do that. So we need a 2 here for the ammonia and a 3 here for the hydrogen. Now, if you've read chapter 7.1, you'll have noticed, or you'll realize very quickly, that these numbers that we just placed there, the coefficients in front of the balanced chemical equation, they tell us a lot about the actual reaction here and what's actually going on. So this actually means that for every 1 molecule of nitrogen, I need 3 molecules of hydrogen to produce 2 molecules of ammonia. While I'm saying molecule, the same thing is true about the number of moles of each of these. So for every 1 mole of nitrogen that we consume, we need to consume 3 moles of hydrogen to produce 2 moles of ammonia. And so we're going to use that little bit there to our advantage in that we're going to be able to use that for some calculations here. So whenever I do these problems, you have no choice. You must start with a balanced chemical equation. So I've got my balanced chemical equation here, and we're going to start with that. Now, what I do when I do these problems is I write down all of the information that I know about any one of my chemicals, and I place it immediately underneath here. So it says here, how many grams of ammonia, so I know I'm going to be looking for grams of ammonia, can be made from 25 grams of nitrogen. So I know that I have 25 grams of nitrogen over here. Now you also actually know how much hydrogen you have. See this word here, excess? Excess means I have enough of this stuff to react all of the nitrogen. So in other words, I'm going to have enough hydrogen in this reacting vessel, wherever this is taking place, to produce ammonia and consume all of the nitrogen gas that I've been given. So that word excess is very, very, very important. It's actually going to become even more important when we look at limiting reagents, which will come next week. So in any case, I've written down the information that I know. Now, for the last couple of weeks, you guys have been practicing with some simple mole calculations. And what you'll realize is that those coefficients that we were talking about, they are not just representative of the number of moles, but they can also represent the ratio in which we have the reacting particles reacting to produce products. And they are not just regular ratios, but they are mole ratios. So in order to do anything in chemistry, you have no choice. You must convert everything into moles. That's why we spent a lot of time over the last couple of weeks learning how to go from mass to moles or number of particles to moles, etc. So I have a mass here, and I need to convert that mass into moles. So I gave you guys a lesson 2 weeks ago about subway science, and so I set my equations up very much like subway systems, and they're easy to follow. So I need to convert this 25 grams into moles. Well, you guys will recall that the 25 grams, in order to go from 25 grams of nitrogen into moles of nitrogen, I need to divide by the molar mass. So I'm going to put a divide here, and I'm going to write out the molar mass of nitrogen. So nitrogen is made of 2 nitrogen atoms. Each nitrogen atom weighs 14.01. So we have a total mass of 28.02 grams per mole. And if I do grams divided by grams per mole, the grams themselves cancel out and I'm left with just moles. And so when I do the actual calculation for this, I end up with 0.8922 moles of nitrogen. So that's how many moles of nitrogen I actually have. Now, if I wanted to figure out how many moles of ammonia I'm producing here, I can set up a simple ratio. So I'm going to set up the ratio to the right-hand side here, but I don't, personally, I don't use this ratio, and you guys can if it makes it easier for you, so there's no problem. So I'm interested in finding out the number of moles of ammonia. So I'm here, and I want to go here. So I have moles of nitrogen. I need to find out moles of ammonia. So I'm gonna show you one way of doing it, and then I'll show you the way that I do it. So the one way that you can do that is to set up a mole ratio off to the side. So I know that for every 2 moles of ammonia, I need 1 mole of nitrogen. And that means that if I have 0.8922 moles of nitrogen, then I'm looking for moles of ammonia. And so I've set up a ratio, a 2-to-1 ratio here. So if I want to find out what X is, I can just take the 0.892, I can multiply it by 2 and then divide it by 1, and I will get a value of 1.784 moles of ammonia that will be produced there from that simple ratio. Now, when I do it, the way I learned was to take the molar ratios that exist from the coefficients in the chemical reaction and place them on this line. So I have a 1-to-2 ratio of nitrogen to ammonia. Now, if I'm looking at the direction in which I'm moving here, I'm moving in this direction according to our subway here, our subway system. So I've gone from mass, I've turned it into moles, moles has turned into moles on the other side, and then I will produce mass in just a second. But in order to do that, what I needed to do as I'm moving along is divide by the first number I interact with and multiply by the second number I interact with. So notice I wrote a 1 here and then I wrote a 2. I'm going to interact with the 1 first. The subway is moving in that direction. I'm going to interact with the 1 first and then the 2. So I'm going to divide by the 1, multiply by the 2, and I'm going to produce this number of moles over here. Now, the nice part about stoichiometry is it's not unidirectional, right? You can go in any direction. So let's say I had this number of moles, the 1.784 moles, and I wanted to figure out how many moles of nitrogen I have. Well, my train would be moving in this direction, and so the first number I would interact with would be the 2, so I would divide by 2, multiply by 1, and that would produce the number that I have on the left-hand side under the nitrogen. And I'll show you how that works in the next question as well. Now I have moles of ammonia, but the question asks how many grams of ammonia can be produced. So you guys, again, over the week, you guys have been doing lots and lots of practice of converting moles into mass. And so how do I do that? I take my number of moles and I multiply it by the molar mass. But I can't use the molar mass of nitrogen because it's not nitrogen that I want to find the mass for. It's ammonia. And so in order to do that, I need to take the molar mass of ammonia. So I have a molar mass of ammonia of 17.04 grams per mole. Now, one thing I do want to point out, and this is a continual error in calculations for students. You may have looked at this, 2 NH3s here, and you might have said, well, the molar mass is 34.08. And you would have said that because this 2 here means 2 NH3s. And I understand the logic there, but remember that this 2 has already been accounted for in the ratio. We don't ever account for it in the number, in the molar mass. So all I'm looking for when I'm calculating these molar masses is the molar mass of one of those, the 1 mole of that particular substance. That's why the units are grams per mole. In any case, when I take the 1.784 moles and I multiply it by the 17.04 grams per mole, my moles will cancel top and bottom, and I will produce a gram up here of 30.41 grams. And that is our final answer there. So let's go on to our next question. So the next question here is, what mass of propane is needed to produce 3.2 grams of carbon dioxide? And it should say in a combustion here. Question mark. So in any case, really simple here. First thing we need to do is we need to set up a balanced chemical equation. So I know that the chemical formula for propane is C3H8, and that's a gas, and it will react with some O2. Remember, that's a standard combustion. So we have some type of fuel, in this case propane, reacts with oxygen, and it always produces carbon dioxide and water. Now, in this particular reaction, we have to balance the chemical reaction, so we're going to go ahead and do that. We need a 3 here, we need a 4 here, and we need a 5 here. So lots of different coefficients here that are going to help us work this through. So in terms of what we know that we have 3.2 grams, or I should say 3.20 grams of carbon dioxide. And it's asking, well, what mass of propane must have been combusted to produce that 3.2 grams of carbon dioxide? So again, no matter what, we always have to get into moles before we start switching between particles here. Because remember, the ratios that exist in the stoichiometry, or in the chemical equation, are molar ratios. They exist as moles. So 1 mole of propane plus 5 moles of oxygen produces 3 moles of carbon dioxide and 4 moles of water. And so in order to do that, I must do exactly what we were doing before. We're going to switch the number of grams into moles. And so in this case, I'm going to divide by the molar mass of carbon dioxide, which is 44.01 grams per mole. Again, grams over grams per mole will produce moles, and I end up with 0.0727 moles here. Now, I don't want moles of carbon dioxide. I'm looking for a mass of propane. So I know I'm here, and I need to make it all the way over to here. I'm going to write out my ratio. My ratio between propane to carbon dioxide is 1 to 3. Now, which way is the train moving? Train is moving in this direction. So I'm going to divide by the first number I interact with, multiply by the second number I interact with, and I'm going to produce the number of moles over on this side, 0.0242 moles. Again, it's asking for the mass, and so I'm in moles right now of propane, so I need to convert to mass of propane. So when I convert to mass, I have to multiply by the molar mass. Now you'll find that the molar mass is almost the same as carbon dioxide at 44.11 grams per mole. And when I multiply that, the moles cancel, and I'm left with just grams, which comes out to 1.07 grams. For those of you who like the other method, by setting up a ratio, it's really simple. You can just simply take the 3 moles of carbon dioxide over 1 mole, I should say right there, CO2, over 1 mole of the propane, C3H8, and that's going to be equivalent to 0.0727 moles of my carbon dioxide over my X moles of propane, and then it's just a matter of solving for X. That'll produce this number here at 0.242. So that's it. We've solved that problem. The answer to the problem was, oops, I don't know why it's doing that, was 1.07 grams. Lastly, we have a problem here, and it says how much of each product. So notice that the language is really important. You have to figure out exactly what we're being asked for. In this case, It's asking us for both products, or at least two products. We don't have an equation yet, so we'll figure that out. It says how much of each product is produced from the neutralization of 10 grams of calcium hydroxide in excess phosphoric acid. So the equation tells, or the question tells us, that there is a neutralization reaction happening, and it's between calcium hydroxide and some phosphoric acid. So if I were to look at what the equation is, we know it's CaOH in brackets 2 plus H3PO4. Now I'm being lazy, these are aqueous. And that will produce some calcium phosphate, aqueous, and some water, H2O liquid. I was also lazy in the other one. These are also gases here. In any case, I'm going to write down what I know. So I want to know how much of each one of these products. So I want to know how much calcium phosphate in grams and how much water in grams I'm going to produce when we have excess phosphoric acid. In other words, so much phosphoric acid that I can react all 10.00 grams of calcium hydroxide. We are going to start looking at equations next week that deal with situations where you don't have excess. In fact, you don't know which one of the reactants is in excess. Those are called limiting reagent problems. We'll do those next week. But in any case, for right now, we have excess H3PO4, or phosphoric acid. So again, we follow the exact same path here. We need to get our grams into moles. How do we do that? We divide by the molar mass of the compound calcium hydroxide, which has a molar mass of 74.09 grams per mole. I don't know why my 9 look like a G, but anyway, 74.09 grams per mole. Grams over grams per mole just produces moles. And so I'm left with 0.1350 moles of calcium phosphate or calcium hydroxide in this. Now it did ask us for the amounts of both products. One of the things we haven't done yet in this particular equation, because I rushed, is not balancing. So we got to make sure that we are balanced here. So I need 3 calcium hydroxides, 2, I don't know why I did that, thank you, 2 phosphoric acids, and 6 waters to produce that balanced chemical equation. We don't need to use those until we get into the molar ratio, which is where we're at right now. So I'm interested, I have the number of moles of calcium hydroxide. I am going to try and figure out the amounts of both of my products. So I'm starting at 0.1350 moles of the calcium hydroxide. I want to know how much calcium phosphate. So I write down my ratio. My ratio is a 3:1 ratio. And my ratio for the second one is a 3:6 ratio. So again, train is moving in this direction over here. And so the first number I interact with I will divide by, and the second number I will multiply by. Same thing down here, divide by 3, multiply by 6. Now some people may not write 3 to 6, they may write 1 to 2 because they're able to reduce it. If you don't reduce it, it's not a big deal. If you do reduce it, it's not a big deal, whatever you like to do. In any case, so we end up with 0.0450 moles of the calcium phosphate and 0.2700 moles of my water here. And then of course we need to get the reaction moving forward and determining how much in terms of mass we have of each. So I'm going to convert my moles here to mass. I need to multiply by the molar mass of the calcium phosphate, which comes out to 310.18 grams per mole. It's pretty heavy. This one over here, when we're going to convert to water, is 18.02 grams per mole of water. And we're multiplying for both. When you do that, you produce the following: 13.96 grams of calcium phosphate produced and 4.865 grams of water that is produced. And so you can see how that flow connects to the subway science that we've been working on ever since. If you guys have any questions, don't hesitate to email me. I want you guys practicing this. There are 7 worksheets on the website, so please help yourselves, and we'll go from there. Thanks, guys.